All right, so let's do a Newton's second law problem. And the situation here is we will have an elevator, and we are going to have somebody, call him Blaine. Blaine will be riding up in the elevator. He steps in, presses the button, and that makes the elevator start moving upwards with a constant acceleration of 2 meters per second squared. And Blaine's mass, let's say, is 70 kilograms, and we want to know what's the normal force of Blaine, on Blaine rather, from the elevator. Okay, so that's our problem. And we know it's a Newton's second law problem, not just because, it's up here in the title, but because we've got mass, we've got acceleration, and we want to know something about force. And so we're interested in the force on Blaine from the elevator. And that means we should probably make Blaine our system, the thing that we're looking at. So once we know what our system is, what the object that we're interested in, we go ahead and draw a free body diagram for that object, which would be Blaine in this case. So there we've got Blaine, and we need to write the forces on Blaine. So forces we've got. This elevator is probably near the surface of the Earth, so we are going to have the force of gravity. He is touching the elevator here, so we're going to have a normal force, that is the surface force. Anytime you've got two objects touching surfaces, you should look for those surface forces, like the normal force and friction. And what else? Well, he's not touching anything else, so we probably don't have any more normal forces going on. We don't have ropes, so no tension. Do we have friction? Well, we only have friction when we're going to get some slipping, or attempt to slip. So the elevator is just going up and down. The surface he's touching is here, so he won't sort of slip up and down the elevator, so no friction force down here. So just the normal force and gravity is all we have. We also have some information about acceleration, so let's also put this near, but not on, our free body diagram. I'll draw it here in a different color to remind myself that acceleration is not a force. And then finally what we need to do, just to make sure we're consistent about signs throughout our problem, is choose a positive direction. I'm going to choose up will be my positive direction, so I'm going to write that in so to remember which of these guys should be positive and which should be negative. Okay, so we got our free body diagram. Now we're ready to use Newton's second law. So Newton's second law is the net force equals the mass times acceleration, and both the net force and acceleration are vectors. And we've only got vertical stuff here, so we don't need to write this both in vertical and horizontal components. We can just write it in vertical. So the forces we've got are the normal force and the gravitational force, and now we need to check signs. The normal force is in the positive direction, so it gets a plus sign. The gravity force, that is opposite the positive direction, so it's negative, so it's going to get a negative sign. And then we have mass times the acceleration, and it's in the positive direction, so just to emphasize that I know that, I'm going to put times plus a. Okay. And you notice I don't have the little vector arrows on top of the forces or the accelerations anymore. And that's because this was a 3D equation, and this is only 1D. This is only in the vertical direction. So I've split it into just a single component here. And then within that dimension, I'm using the plus and negative signs to say whether it's up or it's down in the positive or negative direction in my one component direction. So I've got all the direction information in here already, so I don't need to put those little arrow hats on top anymore. Okay, so what else do we know? We're solving for the normal force, so eventually we're going to get this all by itself, but first we can plug in what we know about gravity. Gravity is always equal to m times little g when you're by the surface of the Earth. And then this is mass times acceleration, because of course mass times positive acceleration is just ma. All right, so we are subtracting mass times gravity from the normal force, which is the thing we want. So let's add mass times gravity to both sides of the equation. So now we have a lovely equation for the normal force. We can actually simplify it just a little bit if we wanted to. Pull out that mass, because it's in both terms over here. And we got the acceleration plus the acceleration due to gravity. So this is telling us that whatever the normal force is, it's going to be more than his weight. Interesting. All right, let's plug in our numbers. Mass, that's 70 kilograms. Acceleration, that's 2 meters per second squared. And then gravity, 9.8, but let's just do 10 meters per second squared, because then I can do the math in my head easy. Okay, so 2 plus 10, that's 12. 12 times 70, that is 840 kilograms meters per second squared. Add these two, they'll still have meters per second squared will be the units of that 12. But kilograms, meters per second squared, that's newtons. Okay, so the normal force on Blaine as the elevator is accelerating up will be 840 newtons. And because 1 newton is about 0.22 pounds, or 1 pound is 1 over that, which is about 4.4-ish newtons. That means that this is roughly, divide by a bit more than 4, 190 pounds. So that is what the normal force on Blaine is going to be when he's going up in the elevator that's accelerating. What if, let's do this actually in a different color. What if the situation were different? What if the acceleration were 0? That is, the elevator were traveling at a constant speed, or it were at rest. If that was the case, we could go right here. The only thing that was changed would be the acceleration would be different. The forces wouldn't change on him, or at least the directions, and the fact that they're there wouldn't change. Then the normal force would, well, this would be 0, because the acceleration is 0, so 0 times anything is 0. And the normal force would just be equal to his weight, or plugging in here, 70 kilograms times 700 meters per second. Remember, we're using that, we're rounding g, so the math is easier. So the normal force would be 700 newtons in that case, which, if we convert to pounds, is divided by a bit more than 4, less than 200, 160-ish pounds. So if the acceleration isn't upwards, but is instead 0, the normal force on Blaine from the elevator is less than what it would be when the elevator is accelerating upwards. And so this is interesting, because what if we put not just Blaine on the elevator, but rather Blaine on a little scale in the elevator, and we were measuring his weight. So that is a scale. So then we have a new force diagram, or rather free body diagram, that we should draw out. So let's go ahead and do that. All right, giving myself a little bit of room. Here's the free body diagram for the scale. And the only thing that'll change here is this won't be the normal force from the elevator anymore. It'll be from the scale. And then what are the forces on the scale? Well, we'll have the gravity force, of course, for the scale. And then this is now gravity on Blaine, so we better just write in Blaine there. So remember, it's Blaine, and this one's on the scale. We'd have a normal force from the elevator on the scale, and then we'd have the Newton's third law pair to this force. This is the normal force on Blaine from the scale, so we would have a normal force from Blaine on the scale. I think I just switched that. So this over here on Blaine, that's the normal force on Blaine from the scale. This one over here is the normal force on the scale from Blaine. And why that's important is this force right here is actually the readout that you get when you step on one of these little spring scales. It reports out what this force is as your weight. So if Blaine were on a scale as he's traveling on this elevator, When the elevator was accelerating up, that would be his weight, 190 pounds. When the elevator was at rest or going at a constant speed, that would be his weight, at least according to the scale. Now, of course, his mass doesn't change. It's 70 kilograms in both cases. And that is how you do a Newton's second law problem. First, you write out a little diagram so you know what's going on. Write down things that you know and what you want. Figure out what object you're looking at. And then draw a free body diagram for that object where you put all the forces on. And you can put acceleration on as well, but make sure it's off to the side so you remember it's not a force. Pick your positive direction and then go ahead and work through all of the algebra that you need to do, being real careful about putting the direction information in at the start. You'll note that when I plugged in for G, I plugged in just the value, just the magnitude. I didn't put in negative because I had already put the direction information here at the very beginning of the problem. And once you do that, then it's just algebra. Get your answer.